Right now, as you're watching this, you're hurtling through space at 67,000 miles per hour aboard a rock that's 4.5 billion years old. But here's what will blow your mind. Even at that incredible speed, it would take you over 40,000 years just to reach the edge of our solar system. And that's not even the shocking part. The real cosmic truth is that the solar system is so vast, so impossibly huge, and surrounded by such hostile emptiness that humanity will be forever trapped within its boundaries. Today we're going on a journey from the Sun to the mysterious Oort Cloud, and I'll show you why the prison of our solar system might be escape-proof. If you're fascinated by the mind-bending scale of our cosmic neighborhood and want to explore more astronomical mysteries, make sure to subscribe to this channel and give a thumbs up. And one quick question. If you could instantly teleport to any location in our solar system, where would you go? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start our journey at the heart of it all, our Sun. This massive ball of plasma contains 99.86% of our solar system's total mass. To put that in perspective, you could fit 1.3 million Earths inside the Sun. But here's what's truly mind-boggling. The Sun's influence extends far, far beyond what we can see. Its gravity reaches out for potentially 2 light years, holding distant frozen objects in orbit that no human eyes have ever seen. The first challenge in understanding our solar system's true size is wrapping our heads around the distances involved. When we talk about space, miles and kilometers become almost meaningless. Instead, astronomers use astronomical units, AU for short. 1 AU equals the average distance from Earth to the Sun, about 93 million miles or 150 million kilometers. This might seem huge, but it's just the beginning of our journey. Mercury, our innermost planet, orbits at just 0.39 AU from the Sun. If our solar system was shrunk down so that Earth's orbit was the size of a basketball court, Mercury would be circling within the free-throw line. Venus, Earth's twisted sister, sits at 0.72 AU. Then comes our home at 1 AU, followed by Mars at 1.52 AU. These inner rocky planets are cosmic neighbors, relatively speaking. But beyond Mars, the scale explodes into something almost incomprehensible. The Asteroid Belt, that region of rocky debris between Mars and Jupiter, spans from about 2.2 to 3.2 AU. Within this zone orbits Ceres, a dwarf planet that contains about 25% of the belt's total mass. But even this vast ring of asteroids is just a stepping stone to the true giants of our solar system. Jupiter, the king of planets, reigns at 5.2 AU from the Sun. This gas giant is so massive that it actually causes the Sun to wobble slightly in its orbit. If Jupiter were hollow, you could fit all the other planets inside it with room to spare. Its powerful magnetic field extends millions of miles into space, creating a miniature solar system with its 4 large Galilean moons and dozens of smaller satellites. But the distances keep growing. Saturn, with its magnificent ring system, orbits at 9.5 AU. Those rings, which look solid from Earth, are actually made of countless chunks of ice and rock, ranging from tiny grains to house-sized boulders. The Cassini spacecraft, which studied Saturn for 13 years before its planned destruction in 2017, revealed that these rings are constantly changing, with spokes, braided patterns, and shepherd moons creating intricate dynamics. Now we enter the realm of the ice giants. Uranus, tipped on its side and rolling around the Sun like a cosmic bowling ball, sits at 19.2 AU. This peculiar world, with its faint ring system and bizarre magnetic field, takes 84 Earth years to complete one orbit. Neptune, the windiest planet with speeds reaching 1,200 miles per hour, lurks at 30 AU. At this distance, the Sun appears as just a very bright star, providing only 1/900th the light that reaches Earth. But we're not even close to the edge yet. Beyond Neptune lies the Kuiper Belt, a vast disk of icy bodies extending from 30 to 50 AU. This region is home to Pluto, which at 39.5 AU takes 248 Earth years to orbit the Sun. When New Horizons flew by Pluto in 2015, it revealed a world far more complex than anyone imagined, with nitrogen glaciers, water ice mountains, and a thin atmosphere that freezes and falls as snow when Pluto moves away from the Sun. The Kuiper Belt contains thousands of objects, including several other dwarf planets like Makemake, Haumea, and Eris. Some of these objects have highly elliptical orbits that take them far beyond the main belt. Sedna, discovered in 2003, has an orbit that takes it from 76 AU at its closest to 937 AU at its farthest. It takes 11,400 Earth years to complete just one orbit, but even Sedna's incredible journey doesn't mark the edge of our solar system. In 2018, astronomers discovered 2018 VG18, nicknamed Farout, at 120 AU from the Sun. Then in 2021, they found 2018 AG37 Farout at 132 AU. These distant objects are so far away that it takes their reflected sunlight over 18 hours to reach us. The Voyager spacecraft, humanity's most distant emissaries, provide a real-world perspective on these mind-numbing distances. Voyager 1, launched in 1977, is now over 159 AU from the Sun, traveling at about 38,000 miles per hour. It took 35 years just to reach the edge of the heliosphere, the bubble of solar wind that surrounds our solar system. At its current speed, it would take Voyager 1 over 70,000 years to reach the nearest star. But here's where our understanding of the solar system's size enters the realm of the truly astronomical. Beyond the Kuiper Belt, beyond the scattered disk objects, lies a theoretical region that dwarfs everything we've discussed so far, the Oort Cloud. This spherical shell of icy bodies is thought to extend from about 2,000 AU to as far as 100,000 AU from the Sun. Some estimates even push it out to 200,000 AU. To put this in perspective, 1 light-year equals about 63,000 AU, meaning the Oort Cloud might extend up to 3 light-years from our Sun. The Oort Cloud is so distant that we've never directly observed it. Its existence is inferred from the orbits of long-period comets that occasionally visit the inner solar system. These cosmic wanderers, like Comet Hale-Bopp or Comet Neowise, take thousands or even millions of years to complete their orbits. They're visitors from the absolute edge of the Sun's gravitational influence, where a gentle nudge from a passing star can send them plummeting toward the inner solar system. Speaking of cosmic scale, if you're amazed by the size of our solar system, wait until you see how it compares to our galaxy. Check out my video called "We Just Found Out How Big the Milky Way Is," and the answer will surprise you. To understand just how tiny our solar system is in the grand scheme of things, the link is in the description and pinned on the comments. Now let's talk about why leaving this vast solar system is so incredibly difficult. The first challenge is simply the distances involved. Even at the speed of light, the absolute cosmic speed limit, it would take over a year to reach the inner edge of the Oort Cloud. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour when falling toward the Sun, but even at that incredible velocity, it would take over 2,000 years to reach the Oort Cloud's inner boundary. The energy requirements for interstellar travel are staggering. To accelerate a spacecraft to even 10% the speed of light would require more energy than humanity currently produces in an entire year. And that's just for a small probe. A crewed mission with life support, supplies, and shielding would require exponentially more energy. The rocket equation, which governs how much fuel you need to achieve a certain speed, becomes a cruel tyrant at these scales. To go faster, you need more fuel, but more fuel means more mass, which requires even more fuel to accelerate. But energy isn't the only barrier. The interstellar medium, the space between stars, is far from empty. It's filled with cosmic rays, high-energy particles that can damage both electronics and human DNA. Our solar system's heliosphere provides some protection from these particles, but once a spacecraft leaves this magnetic bubble, it faces the full fury of interstellar radiation. Shielding against this radiation would add tremendous mass to any spacecraft, making the energy problem even worse. Time is perhaps the cruelest barrier of all. A journey to Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away, would take over 40,000 years with current technology. That's longer than the entire history of human civilization. Even with theoretical fusion rockets that could achieve a few % of light speed, we're still talking about journeys lasting centuries. Multiple generations would live and die aboard a spacecraft before reaching another star. The psychological challenges of such a journey are almost unimaginable. Humans evolved in Earth's diverse environments, with changing seasons, weather, and landscapes. The monotony of a spacecraft environment for decades or centuries could drive people insane. Studies on isolated research stations in Antarctica or long-duration space missions show significant psychological stress after just months. Extending this to centuries is entering uncharted territory for human mental health. There's also the navigation problem. At interstellar distances, even tiny errors compound into massive deviations. A navigation error of just 1 degree would result in missing your target by millions of miles, and you can't just stop and ask for directions in interstellar space. Once you're moving at a significant fraction of light speed, the energy required to stop or change direction becomes astronomical. The communication delay presents another insurmountable challenge. Radio signals travel at light speed, so a message from a spacecraft halfway to Proxima Centauri would take over 2 years to reach Earth, and another 2 years for a response. By the time mission control could respond to an emergency, 4 years would have passed. The crew would be utterly alone, more isolated than any humans in history. But perhaps the most sobering reality is the hostility of interstellar space itself. Our solar system, for all its challenges, is a relatively warm and bright oasis. The temperature in interstellar space approaches absolute zero, minus 459 degrees Fahrenheit. There's no sunlight for solar panels, no planets for gravitational assists, no asteroids for resources. It's an empty, cold, dark void that stretches for trillions of miles. Recent discoveries have made the challenge even more daunting. The Voyager probes have revealed that the boundary between our solar system and interstellar space isn't a clean edge, but a turbulent region where the solar wind meets the interstellar medium. This creates unpredictable magnetic fields and particle densities that we're only beginning to understand. Any spacecraft leaving our solar system would need to navigate this chaotic boundary region. The discovery of interstellar objects like Oumuamua and Borisov has shown us that objects do travel between star systems, but these are simple, rocky or icy bodies, not complex spacecraft with living crews. They've been traveling for millions of years, battered by cosmic rays and micrometeoroids. The fact that we've only detected 2 such objects despite looking for decades shows how empty interstellar space really is. Even our robotic ambassadors face challenges. The Voyager probes, despite their incredible journey, are slowly dying. Their plutonium power sources are decaying, and by 2025, they won't have enough power to operate any scientific instruments. By 2036, they'll fall completely silent. These spacecraft, humanity's farthest travelers, will become inert chunks of metal drifting through the cosmic dark, a sobering reminder of the challenges facing interstellar travel. The physics of propulsion presents fundamental barriers that no amount of engineering cleverness can overcome. Chemical rockets, like those that took us to the Moon, are woefully inadequate for interstellar distances. The best chemical rockets have a specific impulse, essentially their fuel efficiency, of about 450 seconds. To reach even 1% of light speed would require a mass ratio so large that your spacecraft would need to be mostly fuel, with virtually no room for payload, crew, or life support systems. Nuclear propulsion offers better possibilities, but comes with its own challenges. Project Orion in the 1960s proposed using nuclear explosions to push a spacecraft forward. While this could theoretically achieve 3 to 5% of light speed, it would require thousands of nuclear bombs and create massive radioactive contamination. Fusion rockets, still theoretical, might achieve 10% of light speed, but we haven't even mastered controlled fusion for power generation on Earth, let alone for spacecraft propulsion. The Breakthrough Starshot project proposes using powerful lasers to push tiny light sails to 20% of light speed. While this might work for gram-scale probes, it's completely impractical for crewed missions. The acceleration would be lethal to humans, and there's no way to slow down at the destination. These probes would zip through another star system in hours, barely having time to take photos before disappearing back into the void. But let's examine what happens to matter and energy at high speeds. As you approach significant fractions of light speed, relativistic effects become pronounced. Time dilation means that while the crew might experience a journey of decades, centuries would pass on Earth. They would return, if they returned at all, to a world completely transformed. Everyone they knew would be long dead, their culture extinct, their language perhaps forgotten. The interstellar medium becomes increasingly dangerous at high speeds. At 10% of light speed, hitting a dust grain would release energy equivalent to a bomb. At 50% of light speed, even individual hydrogen atoms become deadly projectiles. The faster you go, the more shielding you need, but more shielding means more mass, which means you need more energy to accelerate. It's a vicious cycle with no good solution. Recent observations from the Parker Solar Probe and Solar Orbiter have given us new insights into the solar wind and magnetic fields that protect our solar system. The heliosphere acts like a partial shield against galactic cosmic rays, reducing their intensity by about 70%. Once a spacecraft leaves this protective bubble, the crew would face the full radiation environment of interstellar space. The radiation dose during an interstellar journey would likely be lethal without impossibly heavy shielding. The biological challenges are equally daunting. Humans evolved in Earth's specific environment, our gravity, our day-night cycle, our magnetic field. Long-term exposure to microgravity causes bone loss, muscle atrophy, and cardiovascular problems. We don't know if humans can reproduce in space or if children could develop normally without gravity. A multi-generational journey might end with a crew physically unable to colonize a planet, even if they found one. Consider the closed-loop life support problem. The International Space Station requires regular resupply missions from Earth. A spacecraft on a centuries-long journey would need to recycle everything: air, water, waste, with near-perfect efficiency. Any breakdown in these systems would doom the mission. We've never created a fully closed ecological system that can sustain itself for even years, let alone centuries. The psychological toll of permanent separation from Earth cannot be overstated. Astronauts on the ISS, knowing they'll return home in months, still experience significant psychological stress. The overview effect, seeing Earth as a tiny, fragile ball in the cosmic void, profoundly affects astronauts. Now imagine watching Earth fade to invisibility, knowing you'll never return. The existential isolation would be crushing. Recent studies of extremophiles, organisms that thrive in extreme conditions, have shown that life is remarkably adaptable But even these hardy organisms have limits. The combination of radiation, cold, vacuum, and isolation in interstellar space might be beyond what any Earth-based life can endure. We might need to fundamentally alter human biology to survive such a journey, raising ethical questions about what it means to be human. The discovery of exoplanets has revealed another challenge. We've found over 5,000 planets orbiting other stars, but most are nothing like Earth. Hot Jupiters, super-Earths, planets tidally locked to their stars, the variety is stunning, but mostly hostile to life as we know it. The chances of finding a truly Earth-like planet within reach are vanishingly small. We might travel for centuries only to find worlds we cannot inhabit. Even if we found a habitable planet, the challenges of colonization would be immense. Earth's biosphere is the result of billions of years of evolution. The chemistry of an alien world would be different atmospheric composition, different soil chemistry, possibly different chirality in any existing life forms. Growing Earth crops, raising Earth animals, even breathing the air might be impossible without massive terraforming efforts. The economic argument against interstellar travel is equally compelling. The resources required for a single interstellar mission would dwarf the entire global economy. Who would fund such an endeavor? What possible return on investment could justify the cost? Unless facing extinction on Earth, the economic incentive for interstellar colonization simply doesn't exist. Recent advances in telescope technology have made the scientific case for interstellar travel weaker, not stronger. The James Webb Space Telescope can study exoplanet atmospheres from Earth. Future telescopes might be able to detect biosignatures or even technosignatures from alien civilizations. We can explore the universe with light, gathering vast amounts of information without the impossible challenges of physical travel. The Fermi paradox, if the universe is full of life, where is everybody, might have a simple answer. Perhaps intelligent civilizations realize that interstellar travel is impossible and don't attempt it. They might explore their own solar systems, build space habitats, even dismantle planets for resources, but the gulfs between stars remain forever uncrossed. The great filter might simply be the speed of light and the vast emptiness between stars. Let's dive deeper into the mind-bending mathematics of orbital mechanics that govern our solar system. Every object, from the smallest asteroid to the largest planet, follows precise mathematical laws discovered by Johannes Kepler over 400 years ago. These laws tell us something profound. The farther you are from the Sun, the slower you orbit and the less energy you receive. Neptune, at 30 times Earth's distance from the Sun, receives only 1/900th of the sunlight we enjoy. In the Oort Cloud, the Sun would appear as merely the brightest star in the sky, providing essentially no warmth or energy. The Voyager missions have taught us invaluable lessons about the challenges of leaving our solar system. Voyager 1, after 46 years of travel, has only recently entered interstellar space, and it's still just 0.0024 light-years from the Sun. To put this in perspective, if the distance to Proxima Centauri were represented by a line from Los Angeles to New York, Voyager 1 has traveled about 100 feet. The vastness is simply incomprehensible to human minds, evolved to think in terms of walking distances. Recent discoveries about the interstellar medium have made the challenge even more daunting. The Interstellar Boundary Explorer (IBEX) mission has mapped the boundary between our solar system and interstellar space, revealing a complex and turbulent region. The magnetic fields are stronger than expected, the particle densities are variable, and there are mysterious ribbons of energetic neutral atoms that we don't fully understand. Any spacecraft leaving our solar system would need to navigate this chaotic environment. The power problem becomes increasingly severe as you move away from the Sun. Solar panels, which work well in the inner solar system, become useless beyond Jupiter. The Juno mission to Jupiter has the largest solar panels ever flown on a planetary mission, spanning 66 feet, yet they produce only about 400 watts at Jupiter's distance compared to the 14 kilowatts they would produce at Earth. In interstellar space, solar power is completely impossible. Radioisotope thermoelectric generators, RTGs, which power the Voyager probes and New Horizons, offer a solution but create new problems. These nuclear batteries slowly decay, losing power over time. Voyager's RTGs have lost about 50% of their power output since launch. For a centuries-long interstellar mission, you'd need either massive RTGs that would add tremendous weight or some form of nuclear reactor, which brings its own set of engineering and safety challenges. The navigation challenge in interstellar space is unlike anything we face in the solar system. Within our solar system, we can use the Sun and planets as reference points. We can bounce radio signals off planets for ranging, use their gravity for course corrections, and predict their positions with extreme accuracy. In the void between stars, there are no landmarks, no gravity assists, no way to make course corrections without expending precious fuel. Consider the problem of cosmic rays. These high-energy particles, mostly protons accelerated by supernovae and other cosmic events, constantly bombard everything in space. Earth's magnetic field and atmosphere protect us, and the heliosphere provides some shielding in the outer solar system. But in interstellar space, the flux of cosmic rays is about 4 times higher. Over a journey lasting centuries, this radiation would not only pose health risks but could also damage electronics, degrade materials, and even affect the structural integrity of the spacecraft. The recent discovery of interstellar dust has added another layer of complexity. The Cassini mission detected interstellar dust particles entering our solar system, and analysis shows they're different from the dust in our solar system. This alien dust is smaller, faster moving, and has a different composition. A spacecraft traveling at high speed through regions of dense interstellar dust could face significant erosion of its hull and critical components. Time itself becomes an enemy on interstellar journeys. Materials degrade, seals fail, metals fatigue. The longest operating spacecraft, Voyager 1 and 2, are experiencing numerous failures after less than 50 years. Thrusters are clogging, instruments are failing, and computer memory is corrupting. Designing systems that could operate reliably for centuries is beyond our current engineering capabilities. The communication infrastructure needed for interstellar missions presents its own impossibilities. Radio signals weaken with the square of distance. The Deep Space Network, Earth's most powerful communication system, is already struggling to maintain contact with Voyager at just over 20 billion kilometers. At interstellar distances, even with massive improvements in technology, data rates would be measured in bits per day, not the megabits per second we're accustomed to. Let's talk about the reality of generation ships, spacecraft where multiple generations would live and die during the journey. The minimum viable population to avoid inbreeding is estimated at around 160 people, but that assumes perfect breeding management. A safer number would be several thousand. These people would need living space, recreation areas, schools, hospitals, essentially a small city in space. The mass requirements would be staggering. The sociological challenges of generation ships are perhaps even more daunting than the technical ones. How do you maintain a stable society for centuries in a confined space? How do you ensure that the grandchildren of the original crew still want to complete a mission they didn't choose? History is full of societies that have collapsed or radically changed over much shorter timescales. The idea that we could maintain a focused, stable society in a tin can for centuries is perhaps the most unrealistic aspect of interstellar travel. Recent studies of isolated communities on Earth provide sobering insights. Research stations in Antarctica, despite regular supply deliveries, and the knowledge that isolation is temporary, experience significant psychological problems. Rates of depression, anxiety, and conflict increase dramatically. Now imagine this isolation is permanent, with no possibility of rescue or resupply, extending for generations. The psychological toll would be unprecedented. The discovery of rogue planets, worlds ejected from their star systems and wandering through interstellar space, has revealed another hazard. There could be billions of these dark worlds in our galaxy, invisible and undetectable until you're almost upon them. A collision with a rogue planet or even a close encounter that alters your trajectory would doom an interstellar mission. The empty space between stars isn't as empty as we once thought. The material science challenges for interstellar travel push beyond anything we've achieved. In the vacuum of space, materials behave differently than on Earth. Metals can cold weld together, plastics become brittle from radiation exposure, and even advanced composites degrade over time. The longest we've kept any spacecraft operational is less than 50 years, and those are simple robotic probes. A crewed interstellar vessel would need to maintain life support, propulsion, navigation, and countless other systems for centuries without access to replacement parts or raw materials. Recent experiments on the International Space Station have revealed disturbing trends. Bacteria behave differently in microgravity, often becoming more virulent. Some bacteria form thicker biofilms that are harder to remove. Fungi grow faster and in unexpected patterns. Over centuries, these microorganisms could evolve in unpredictable ways, potentially becoming dangerous to the crew or damaging to the spacecraft systems. We might face diseases that don't exist on Earth, with no way to get medical help. The asteroid belt, often depicted in science fiction as a dense field of rocks, is actually mostly empty space. If you were standing on one asteroid, the next nearest might be hundreds of thousands of miles away. This emptiness extends throughout our solar system and becomes absolute in interstellar space. The idea of finding resources along the way, stopping at asteroids or comets for supplies, becomes impossible once you leave the Oort Cloud. You must carry everything you need for the entire journey. Let's consider the latest findings about our solar system's movement through the galaxy. Our entire solar system is orbiting the galactic center at about 514,000 miles per hour, completing one orbit every 230 million years. As we move through the galaxy, we pass through different regions with varying densities of stars, gas, and dark matter. An interstellar journey would need to account for these galactic-scale movements, adding another layer of complexity to navigation. The discovery of Planet 9, still hypothetical but supported by strong gravitational evidence, shows we don't even fully understand our own solar system yet. This proposed planet, thought to be 5 to 10 times Earth's mass and orbiting at 400 to 800 AU from the Sun, would take 10,000 to 20,000 years to complete one orbit. If we haven't even found all the major planets in our own solar system, how can we hope to navigate the unknowns of interstellar space? Recent studies of tardigrades, those microscopic water bears that can survive extreme conditions, have shown that even the toughest organisms have limits. While tardigrades can survive the vacuum of space for limited periods, long-term exposure to cosmic radiation still damages their DNA beyond repair. If the toughest life forms we know can't survive indefinitely in space, what hope do fragile humans have? The energy density problem is worth examining more closely. The best chemical rockets have an energy density of about 13 megajoules per kilogram. Nuclear fission increases this to about 80 trillion megajoules per kilogram. But even antimatter, the ultimate fuel with perfect mass-to-energy conversion, would require tons of antimatter for an interstellar mission. We currently produce antimatter in quantities measured in individual atoms at a cost of trillions of dollars per gram. The Parker Solar Probe, humanity's fastest spacecraft, required a complex trajectory using 7 Venus flybys over 7 years just to achieve its record-breaking speed, and this is just to reach the Sun using the Sun's gravity to accelerate. In interstellar space, there are no gravity assists, no clever orbital mechanics to help you. Every meter per second of velocity change must come from your engines, requiring fuel you must carry from the start. Consider the data storage problem for a multi-generational journey. All of human knowledge, culture, and history would need to be preserved digitally, but digital storage degrades over time. Bit rot, cosmic ray strikes, and hardware failures would slowly corrupt the data. After centuries, would the colonists still have access to Earth's cultural heritage? Would they remember why they left or where they came from? The loss of cultural continuity could be as devastating as any technical failure. The recent discovery of phosphine in Venus's atmosphere, though controversial, highlights another issue. If we might have life in our own solar system that we haven't detected yet, how can we be sure any exoplanet is truly habitable? We might travel for centuries to a planet that looks Earth-like from telescopes, only to discover it's toxic to Earth life in ways we couldn't detect from light years away. The Breakthrough Listen project, searching for signs of intelligent life, has scanned thousands of stars without finding any confirmed artificial signals. This silence might be telling us something profound. Perhaps interstellar travel is so difficult that civilizations give up trying. They might turn inward, building space habitats in their own solar systems, creating virtual worlds, or pursuing other paths we can't imagine. The galaxy's silence might be the sound of civilizations that realized interstellar travel is impossible. Time lag in decision-making becomes critical on long journeys. If a problem arose halfway to Proxima Centauri, it would take over 2 years for the crew's message to reach Earth and another 2 years for Earth's response to reach the ship. By then, 4 years would have passed. The crew would need to be completely autonomous, making life or death decisions with no possibility of consultation with Earth experts. The manufacturing problem is equally daunting. A self-sufficient interstellar spacecraft would need the ability to manufacture everything from basic tools to complex electronics. This would require raw materials, processing facilities, and expertise in hundreds of fields. The spacecraft would need to be a miniature civilization, complete with mining, refining, manufacturing, and recycling capabilities. The mass and complexity would be staggering. Recent observations of Voyager's star, which showed mysterious dimming patterns that some speculated might be alien megastructures, turned out to be dust clouds. This reminds us that the universe is full of phenomena we don't understand. An interstellar spacecraft might encounter completely unexpected hazards, dark matter clumps, primordial black holes, or physics we haven't discovered yet. The unknown unknowns could be the greatest danger of all. The cellular and molecular damage from prolonged space exposure presents barriers we're only beginning to understand. Recent studies on astronauts show that spaceflight causes changes at the genetic level. Telomeres, the protective caps on chromosomes, behave erratically in space. Some lengthen, some shorten, and these changes persist after returning to Earth. Over a multi-generational interstellar journey, these genetic changes could accumulate, potentially creating humans so altered they might not even be the same species anymore. Let's examine what we've learned from the New Horizons mission to Pluto and beyond. Launched in 2006 at the highest speed of any spacecraft leaving Earth, it still took 9.5 years just to reach Pluto. After its Pluto flyby, it continued to the Kuiper Belt object Arrokoth, which took another 4 years. This mission, covering just a tiny fraction of our solar system, required nearly 14 years. The timescales for interstellar travel are incomprehensibly longer. The gravitational influence of our Sun extends far beyond what most people realize. The Hill sphere, the region where the Sun's gravity dominates over galactic tides, extends to about 1 to 2 light-years. This means objects within this vast sphere are gravitationally bound to our Sun. But here's the kicker. At the outer edge of this influence, orbital velocities are so slow that objects take millions of years to complete one orbit. The Sun's grip is weak but far-reaching. Recent computer simulations of interstellar colonization paint a sobering picture. Even assuming self-replicating robotic probes that could build copies of themselves at each star system, it would take millions of years to colonize even a small portion of the galaxy. For biological beings traveling in generation ships, the timeline extends to tens of millions of years. Civilizations rise and fall in thousands of years. The species attempting colonization might evolve into something unrecognizable before the process completes. The discovery of binary star systems' prevalence adds another complication. Over half of all star systems are binary or multiple star systems. Planets in such systems experience complex gravitational dynamics, variable stellar radiation, and potentially unstable orbits. Our single star system, with its relatively circular planetary orbits, is actually somewhat unusual. Many destinations we might aim for could be gravitationally chaotic environments hostile to colonization. Consider the practical reality of maintaining human civilization on a generation ship. You'd need teachers to educate children, doctors to treat illnesses, engineers to maintain systems, farmers to grow food, and hundreds of other specializations. But with a limited population, what happens when your only heart surgeon dies, or your last expert on life support systems? Knowledge would inevitably be lost over generations, potentially dooming the mission through gradual degradation of expertise. The latest research on closed ecological systems reveals how difficult they are to maintain. Biosphere 2, the largest closed system ever built, faced numerous problems despite being on Earth with access to external support. Oxygen levels dropped, carbon dioxide spiked, species went extinct, and the system required outside intervention to survive. Creating a stable ecosystem that could last centuries in a spacecraft seems nearly impossible with our current understanding. The Van Allen radiation belts around Earth give us a taste of the radiation challenges in space. These belts of charged particles trapped by Earth's magnetic field can damage satellites and endanger astronauts. Jupiter's radiation belts are far worse. The Juno spacecraft receives the equivalent of 100 million dental X-rays during each orbit. Now imagine the cumulative radiation exposure over centuries of interstellar travel with no planetary magnetic field for protection. Recent discoveries about quantum biology suggest life depends on quantum effects that might not work the same way in the different radiation and gravitational environments of space. Photosynthesis, enzyme function, and possibly even consciousness involve quantum processes. These delicate quantum states could be disrupted by cosmic radiation or the absence of Earth's specific electromagnetic environment. Life itself might be more Earth-dependent than we realize. The economics of keeping a solar system economy running versus interstellar expansion makes the choice clear. The asteroid belt contains enough resources to support quadrillions of humans in space habitats. Jupiter's moons contain vast amounts of water. Saturn's moon Titan has lakes of liquid methane that could serve as rocket fuel. We could build a thriving civilization throughout our solar system without ever needing to tackle the impossible challenge of interstellar travel. The speed of chemical reactions changes with temperature and pressure. In the near absolute zero of interstellar space, many chemical processes would slow dramatically or stop entirely. Lubricants would freeze, batteries would fail, and even basic material properties would change. The spacecraft would need to maintain Earth-like conditions not just for the crew, but for its own mechanical and chemical systems, requiring enormous amounts of energy. Let me share a sobering calculation. If we could magically transport humans to every star system within 100 light years, and each system could support 10 billion people, we'd have room for about 40 trillion humans. That sounds like a lot, but a single solar system with extensive space habitats could support similar numbers. The stupendous effort of interstellar colonization yields no more living space than fully developing our own solar system. The discovery of gravitational waves has given us a new tool to study the universe, but it also reveals new challenges. Massive objects accelerating through space create ripples in space-time itself. An interstellar spacecraft accelerating to high speeds would create its own gravitational waves, however tiny. In the perfect silence of interstellar space, could advanced alien civilizations detect these waves? Would announcing our presence be wise or dangerous? Recent studies of extremophiles in Earth's deepest mines and ocean trenches show that life requires energy gradients to survive. Organisms extract energy from chemical or thermal differences in their environment. In the uniform cold of interstellar space, with no energy gradients to exploit, even the hardiest organisms would eventually die. Life needs energy flows, and interstellar space is essentially a vast desert with no oases. The problem of spare parts and maintenance becomes insurmountable over centuries. Every mechanical system has a mean time between failures. With millions of components, something would always be breaking. You'd need spare parts for everything, but spare parts degrade too. You'd need the ability to manufacture new parts, but manufacturing equipment also breaks down. It's an endless regression of maintenance requirements that compounds over time. The psychological reality of permanent separation from Earth goes deeper than simple homesickness. Humans have evolved with specific environmental cues: the 24-hour day-night cycle, seasonal changes, the specific spectrum of sunlight, even the particular blue of Earth's sky. These aren't just aesthetic preferences, they're deeply wired into our circadian rhythms, hormone production, and mental health. Studies on Antarctic research stations, despite lasting just months and with guaranteed return, show significant increases in depression, anxiety, and cognitive decline. Scale this to permanent exile from Earth, and we enter uncharted territory for human psychology. Recent observations from the Solar Dynamics Observatory have revealed the complexity of our Sun's behavior. Solar flares, coronal mass ejections, and the 11-year solar cycle all affect space weather throughout our solar system. We've learned to predict and prepare for these events within our solar system, but other stars have their own patterns, possibly more violent and unpredictable. Proxima Centauri, our nearest neighbor, is a flare star that regularly erupts with radiation that would sterilize any nearby planets. The devil you know might be better than the devil you don't. The Oort Cloud represents a boundary that's more than just physical. It marks the transition from the familiar to the truly alien. Objects in the Oort Cloud are so loosely bound to the Sun that a passing star can easily disrupt their orbits. In fact, the Oort Cloud is likely being constantly stripped and replenished through gravitational interactions with the galaxy. It's a dynamic, ever-changing frontier that we barely understand, yet we'd need to traverse it completely to reach another star. Let's talk about the reality of artificial gravity. Science fiction loves rotating spacecraft that create centrifugal force to simulate gravity, but the engineering challenges are immense. The structure would need to be huge to avoid nauseating Coriolis effects, at least 100 meters in diameter. It would need to rotate continuously for centuries without maintenance, without wobbling, without catastrophic failure. Every rotating seal, every bearing, every structural joint becomes a potential point of failure that could doom the mission. The recent discovery of interstellar objects Oumuamua and Borisov has taught us something crucial. These objects have been traveling through interstellar space for millions or billions of years, and they're basically tumbling rocks or chunks of ice. If simple, solid objects can barely survive interstellar travel intact, what chance does a complex spacecraft with millions of components have? Oumuamua's unusual acceleration as it left our solar system still puzzles scientists, reminding us that interstellar space might hold surprises we haven't anticipated. Consider the manufacturing challenge in concrete terms. A single computer chip requires dozens of rare elements, ultra-pure materials, and fabrication facilities that cost billions of dollars on Earth. A generation ship would need to produce not just computer chips, but everything from basic screws to complex pharmaceuticals. You'd need mining equipment, refineries, chemical plants, clean rooms, and the expertise to operate all of them. It would be like asking a small town to be completely self-sufficient in producing everything from smartphones to heart medication. The latest data from the Gaia Space Telescope has mapped the positions and movements of over 1 billion stars in our galaxy. This has revealed that our solar system doesn't travel through empty space, but through a complex, dynamic environment. We're currently passing through the local interstellar cloud, a region of slightly denser gas about 30 light-years across. In about 20,000 years, we'll exit this cloud and enter a different environment. An interstellar spacecraft would need to navigate through multiple such regions, each with different densities, temperatures, and possibly unknown hazards. Time becomes strange on multi-generational journeys. The original crew would have direct memories of Earth, but their children would know it only through stories and recordings. By the third or fourth generation, Earth would be mythology. Would they still feel bound by the mission their ancestors started? Would they even believe Earth existed? We see this cultural drift in just a few generations on Earth. Over centuries in isolation, the changes would be profound. The medical challenges compound over time. Earth's medical knowledge would become increasingly irrelevant as the crew adapts to spacecraft conditions. New diseases might evolve, childhood development might differ in artificial gravity, and medical equipment would degrade. Without access to Earth's vast medical infrastructure, pharmaceutical industry, and research community, medicine would likely regress to much simpler practices. A treatable condition on Earth might be a death sentence on a generation ship. Recent studies of the Deep Space Network, which communicates with our most distant spacecraft, reveal the practical limits of interstellar communication. The network's 70-meter dishes can barely maintain contact with Voyager using transmitters no more powerful than a refrigerator light bulb. At interstellar distances, even with massive improvements in technology, bandwidth would be so limited that sending a single image could take years. Real-time communication would be impossible, making the crew truly alone. The discovery of super-Earths, planets larger than Earth but smaller than Neptune, has complicated our search for habitable worlds. These planets, which don't exist in our solar system, are actually the most common type in the galaxy, but their stronger gravity would make landing and taking off extremely difficult. A planet with just 50% more gravity than Earth would require rockets far more powerful than anything we've built just to reach orbit. Colonists might be permanently trapped on the surface. Let's examine the asteroid mining proposals that some suggest could support interstellar travel. While asteroids contain valuable resources, extracting and processing them in the vacuum of space is extraordinarily difficult. The OSIRIS-REx mission collected just 60 grams of material from asteroid Bennu at a cost of over $1 billion. Scaling this up to industrial levels would require infrastructure that doesn't exist and might not be economically viable even within our solar system, let alone for supporting interstellar missions. The cosmic ray problem gets worse the longer you're exposed. These high-energy particles don't just cause radiation sickness, they create cascades of secondary particles when they hit spacecraft hulls. Over time, this bombardment would make the hull itself radioactive. After centuries of exposure, the spacecraft structure could become so radioactive that it poses a health hazard to the crew, creating an inescapable source of radiation that no amount of shielding can block because the shielding itself becomes the problem. The collision risk in interstellar space might seem negligible given the emptiness, but the consequences of even one impact could be catastrophic. At 10% the speed of light, a collision with a particle the size of a grain of sand would release energy equivalent to a nuclear bomb. We can track and avoid large objects in our solar system, but in interstellar space, by the time you detect something, it's too late to avoid it. The faster you go to shorten the journey, the more deadly every piece of debris becomes. Recent computer models of stellar evolution have shown us that stars are far less stable than we once thought. Our Sun is remarkably calm compared to most stars. The Kepler Space Telescope observed thousands of Sun-like stars and found that superflares, eruptions 10,000 times more powerful than typical solar flares, occur on Sun-like stars more frequently than expected. We've been lucky with our stable Sun, but other stars might regularly sterilize their planets with radiation bursts we can't predict or defend against. The concept of the tyranny of the rocket equation becomes overwhelming at interstellar scales. This equation, developed by Konstantin Tsiolkovsky, shows that the amount of fuel needed increases exponentially with desired velocity. To reach just 5% of light speed, 99% of your spacecraft's initial mass would need to be fuel. To reach 10%, you'd need a fuel-to-payload ratio so extreme that your spacecraft would essentially be a giant fuel tank with a tiny capsule attached. And this assumes perfect efficiency, which is impossible. Let's consider what happens to human society over the timescales involved. The Roman Empire, one of history's longest-lasting civilizations, existed for about 1,500 years. The journey to another star would take longer than the entire span from ancient Rome to today. Languages would evolve beyond recognition, religions would transform or disappear, and the very purpose of the mission might be forgotten or rejected. The idea that we could maintain a coherent society and mission focus over such timescales flies in the face of all historical evidence. The latest discoveries about DNA damage in space are sobering. The NASA twin study comparing astronaut Scott Kelly, who spent a year in space with his identical twin Mark, who stayed on Earth, revealed changes in gene expression, cognitive decline, and genomic instability. Some of these changes persisted after return to Earth. Over multiple generations in space, genetic damage would accumulate, potentially leading to increased cancer rates, reduced fertility, and other health problems that could doom a colony before it reaches its destination. Recent observations of brown dwarfs, failed stars too small to sustain fusion, have revealed they're more common than we thought. These dark objects, nearly invisible until you're close to them, litter interstellar space. A close encounter with a brown dwarf could gravitationally disrupt a spacecraft's trajectory, sending it off course with no way to recover. These invisible gravitational mines are impossible to map completely and represent another unknown danger in interstellar space. The cultural preservation problem is more severe than most realize. Digital storage degrades, physical books deteriorate, and human memory is fallible. After centuries, would the colonists still have access to humanity's great works of art, literature, music, and science? Or would they arrive at their destination culturally impoverished, having lost the heritage that makes us human? The Library of Alexandria's destruction shows how easily knowledge can be lost even on Earth. In the isolation of space, such losses would be irreversible. Consider the ethical implications of generation ships. The first generation chooses to leave Earth, but their children and all subsequent generations have no choice. They're born into a mission they didn't select, condemned to live and die in a tin can flying through void, never experiencing rain, wind, beaches, mountains, or any of the natural world that shaped human evolution. Is it ethical to condemn unborn generations to such an existence? This moral question might be as insurmountable as the technical challenges. The discovery of the Laniakea supercluster, our local group of 100,000 galaxies spanning 500 million light-years, puts our ambitions in perspective. Our entire galaxy is just a tiny part of this structure, which itself is just one of millions of superclusters in the observable universe. The idea that humans who have trouble cooperating on a single planet could spread across even a tiny fraction of one galaxy seems like hubris of the highest order. Recent studies of microbial evolution in spacecraft have revealed alarming trends. Bacteria on the ISS evolve rapidly, developing resistance to antibiotics and changing their behavior in ways we don't fully understand. Over centuries, the microbial ecosystem of a generation ship could evolve in unpredictable directions. Beneficial bacteria might become pathogenic, essential microbiomes might collapse, or new diseases might emerge that Earth medicine couldn't anticipate or treat. The power generation problem becomes acute over long timescales. Solar panels degrade and become useless far from any star. Nuclear reactors require fuel and maintenance. Fusion reactors, if we ever perfect them, still need deuterium and tritium. Even hypothetical antimatter engines would need antimatter fuel that we have no way to produce in sufficient quantities. After centuries, any power system would degrade, and without power, the mission dies in the cold darkness of space. Let's talk about the navigation precision required. To hit a target star system from light years away is like shooting a bullet from New York and hitting a specific building in Los Angeles, except the target is moving, the bullet takes centuries to arrive, and you can't adjust the aim after firing. The slightest error in initial trajectory, the gravitational pull of an unseen object, or any number of other factors could cause you to miss entirely, dooming the mission to eternal wandering in interstellar space. The recent discovery of rogue planets between stars adds another dimension to the hazard list. These dark worlds, ejected from their original star systems, wander invisible through interstellar space. There could be billions of them in our galaxy. Hitting one would obviously destroy a spacecraft, but even a near miss could gravitationally alter the trajectory enough to ruin the mission. These invisible gravitational hazards are impossible to map completely. The maintenance of genetic diversity presents an unsolvable paradox. Too small a population leads to inbreeding and genetic defects. Too large a population exceeds the spacecraft's life support capacity. Genetic engineering might help, but it raises ethical questions and could have unintended consequences that only manifest generations later. The minimum viable population for a healthy human colony is hotly debated, with estimates ranging from hundreds to tens of thousands. The fundamental physics of information transfer presents yet another barrier. Even if we could travel to another star, maintaining any connection with Earth becomes meaningless over such distances. At light speed, a message to Proxima Centauri takes 4.24 years each way. A simple conversation, "Hello, how are you?" "Fine, thanks," to you would take nearly a decade. For more distant stars, we're talking about centuries for a single exchange. The colony would be more isolated than any humans in history, cut off not just by distance, but by time itself. Recent advances in our understanding of planetary formation have revealed how unique our solar system might be. The ALMA telescope has observed protoplanetary disks around young stars, showing that most planetary systems form differently than ours. Hot Jupiters spiraling close to their stars, super-Earths in tight orbits, and chaotic gravitational interactions seem to be the norm. Our solar system's stable, nearly circular orbits might be extraordinarily rare. The chances of finding another system as hospitable as ours within reachable distance approach zero. The Spitzer Space Telescope's observations before its retirement revealed that most stars in our galaxy are red dwarfs, small, cool stars that pose unique challenges for habitability. Planets in the habitable zone of red dwarfs would be tidally locked, with one side in eternal day and the other in eternal night. They'd be bombarded by stellar flares and subjected to extreme temperature differences. The most common type of star in the universe might be fundamentally unsuitable for Earth-like life. Let's examine the reality of terraforming, often proposed as a solution to hostile exoplanets. Mars, right here in our solar system, would require warming the planet, thickening its atmosphere, creating a magnetic field, and importing vast amounts of water and nitrogen. This would take thousands of years with technology we don't have. Now imagine trying to terraform an exoplanet light years away with unknown composition, gravity, and conditions. It's fantasy, not science. The latest studies on the effects of cosmic radiation on electronics reveal a ticking time bomb for any interstellar mission. Cosmic rays cause bit flips in computer memory, degradation of solar panels, and breakdown of insulation. Over centuries, these effects compound. The spacecraft's computers would gradually become unreliable, navigation systems would drift, and critical systems would fail in cascading failures that no amount of redundancy could prevent. Recent discoveries about the role of Jupiter in our solar system highlight another challenge. Jupiter acts as a vacuum cleaner, its massive gravity deflecting many comets and asteroids that might otherwise impact Earth. This protection has been crucial for life's development on Earth. Other planetary systems might lack such protectors, making any potentially habitable planets subject to constant bombardment. We might travel for centuries only to find worlds under constant asteroid assault. The problem of language and communication over generations reveals deep challenges. Languages evolve rapidly. English from just 500 years ago is barely comprehensible to modern speakers. Over centuries of isolation, the generation ship's language would diverge from Earth's. Technical manuals, scientific knowledge, and cultural works would need constant translation and interpretation. Critical knowledge could be lost simply through linguistic drift. Consider what we've learned from the Dawn mission to Vesta and Ceres. These are significant bodies right here in our solar system, yet they surprised us with unexpected geology, chemistry, and potential subsurface oceans. If objects in our own backyard can surprise us so much, imagine the unknowns awaiting in another star system. We might prepare for centuries for conditions that turn out to be completely different from our predictions. The latest research on extremophils has revealed both possibilities and limitations. Yes, life can survive in extreme conditions, in boiling water, in acid, in nuclear reactors. But every extremophile is specialized for specific conditions. There's no universal survivor that can handle all extremes. The combination of radiation, cold, vacuum, and isolation in interstellar space might be beyond what any Earth life can endure, even with genetic engineering. The social stratification inevitable on a generation ship presents another unsolvable problem. Who decides who does what job? Who gets to reproduce? Who makes decisions about resource allocation? History shows that isolated communities often develop rigid hierarchies, abuse of power, and social breakdown. The Stanford Prison Experiment and similar studies show how quickly normal people can become abusive when given power in isolated conditions. A generation ship could become a flying dystopia. Recent observations of stellar nurseries by the James Webb Space Telescope show that star formation is even more violent and chaotic than we thought. Young stars blast their surroundings with intense radiation and stellar winds, stripping atmospheres from nearby planets. The journey to another star might end in a system still undergoing violent formation processes, uninhabitable for millions of years. We could arrive at a cosmic construction site rather than a new home. The discovery of ultra-hot Jupiters, gas giants, with temperatures exceeding 3,000 degrees, shows the extreme conditions common in other systems. These planets orbit so close to their stars that they rain liquid iron and have winds of glass. Their presence often destabilizes the orbits of other planets in the system. Many star systems are fundamentally hostile to Earth-like planets, dominated by these orbital bullies. Let's talk about the decision-making paralysis that would develop over time. The first generation has Earth's authority and expertise to consult. The second generation has their parents' memories. But by the 10th generation, they'd be making life or death decisions based on centuries-old Earth knowledge that might no longer apply. They couldn't consult Earth experts due to communication delays. They'd be flying blind, making irreversible choices with incomplete information. The latest studies on bone loss in microgravity show that even with hours of daily exercise, astronauts lose 1 to 2% of bone mass per month. Over years, this leads to osteoporosis-like conditions. In partial gravity or artificial gravity from rotation, we simply don't know what happens to human development. Children born and raised in these conditions might be unable to ever walk on a planet with Earth-like gravity. We might be creating humans who can never colonize worlds, only live in spacecraft. The problem of cosmic dust accumulation is underappreciated. High speeds, even individual atoms, act like sandblasting. Over centuries, this would erode hull surfaces, cloud windows, degrade sensors, and potentially breach the hull. The spacecraft would need constant external repairs, but EVAs in interstellar space at high velocity would be impossibly dangerous. The ship would slowly be worn away with no way to stop it. As we reach the end of our cosmic journey, let me share the most profound realization of all. The Fermi paradox, where is everybody, might have the simplest answer imaginable. They're all trapped in their own solar systems, just like us. Every intelligent civilization that has ever evolved might have looked at the stars with the same dreams we have, done the same calculations we've done, and reached the same crushing conclusion. The universe hasn't built a playground for interstellar civilizations. It's built an archipelago of isolated islands, forever separated by impossible oceans of darkness. Recent philosophical discussions about the Great Filter suggest we might be looking at it wrong. The filter isn't some catastrophic event that destroys civilizations. It's simply the laws of physics themselves. The speed of light, the vast distances, the hostile environment of interstellar space, these aren't challenges to be overcome, but fundamental barriers written into the fabric of reality. We're not failing to become an interstellar species. We're succeeding at recognizing the impossible. The latest data from the Event Horizon Telescope, which gave us our first image of a black hole, reminds us of the extreme forces at play in our universe. That black hole in M87 is 55 million light-years away, yet we can study it in detail from Earth. This is the paradox of our situation. We can see across billions of light-years, but can't travel even one. We're cosmic observers, not cosmic travelers, and perhaps that's our true destiny. Let's put our solar system in its true perspective. If the Milky Way galaxy was shrunk down to the size of North America, our entire solar system would be smaller than a pinhead. The Oort Cloud, that vast sphere marking our system's edge, would be barely visible under a microscope. And the distance to the nearest star, about 200 feet. In this scale model, human spacecraft have traveled less than the width of a human hair. The recent discovery of the most distant object in our solar system, nicknamed Farout, orbiting at 132 AU, reminds us we're still discovering our own cosmic backyard. We've found less than 1% of the objects in the Kuiper Belt. The Oort Cloud remains entirely theoretical, its existence inferred but never directly observed. We haven't even fully explored our own solar system, yet we dream of others. Consider what the solar system offers us that we haven't yet claimed. The asteroid belt contains enough iron to build space habitats housing trillions of humans. Jupiter's moon Europa has more water than all Earth's oceans combined. Titan has lakes of liquid methane that could fuel spacecraft for millennia. The helium-3 on the moon could power fusion reactors for thousands of years. We're like people starving in a fully stocked warehouse, dreaming of breaking out to find food. The James Webb Space Telescope has shown us infant galaxies at the edge of time, revealed atmospheres of distant exoplanets, and peered into stellar nurseries where new worlds are born. We can study the entire universe from our tiny platform. Every photon that reaches our telescopes has traveled across cosmic gulfs to tell us its story. We don't need to travel to the stars come to us in the form of light that carries all their secrets. Recent calculations about the future of our solar system offer a strange comfort. The Sun will remain stable for another 5 billion years, longer than life has existed on Earth. That's enough time for humanity to evolve into something unrecognizable, to build wonders throughout our solar system, to think thoughts we can't imagine. We don't need other stars. We have barely begun to use the one we've got. The philosophical implications cut deep. We are the universe becoming aware of itself, but that awareness comes with limits. We can know the cosmos, but not explore it. We can see other worlds, but not touch them. We're like a child pressed against a shop window, able to see all the toys, but unable to enter. This isn't tragedy. It's the human condition writ large across the cosmos. Every atom in your body, except hydrogen, was forged in the heart of a dying star. You are literally made of stardust, organized temporarily into a pattern capable of contemplating its origins. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it traveled through interstellar space to get here. In a sense, you've already completed an interstellar journey. You're made of matter that successfully traveled between stars. It just did it before assembling into you. The realization that we're trapped in our solar system should fill us with awe, not disappointment. We're on a spacecraft, Earth, that's been successfully navigating the cosmos for 4.5 billion years. It has perfect life support, radiation shielding, and a power source good for billions more years. It's already traveling through space at fantastic speeds, carrying us on a journey through time. We don't need to build an interstellar spacecraft, we're already on one. Recent studies of the Earth-Moon system show how perfectly balanced our situation is. The Moon stabilizes Earth's axis, giving us regular seasons. It creates tides that may have been crucial for life's evolution. Its gravity helps protect us from asteroids. This isn't just a planet, it's a perfectly tuned system for supporting life. The chances of finding another such system within reachable distance are vanishingly small. We already live in paradise. The truth is, the solar system is our inheritance, our territory, our future. From the scorching surface of Mercury to the frozen depths of the Kuiper Belt, from the sulfur volcanoes of Io to the methane rain on Titan, we have worlds enough for millions of years of exploration and colonization. We have resources beyond imagination, energy from the sun that will last billions of years, and room for quadrillions of humans in space habitats we've yet to build. Yes, we will never leave our solar system. The physics is implacable, the distance is impossible, the challenge is insurmountable, but instead of mourning the stars we'll never reach, we should celebrate the incredible cosmic oasis we've been given. We have a sun that nurtures us, planets that inspire us, moons that beckon us, and asteroids that could house our descendants for eons to come. In the end, perhaps the prison metaphor is wrong. We're not trapped in our solar system, we're cradled by it. The vast distances that isolate us also protect us. The same physics that prevents us from leaving also ensures that no cosmic horror can easily reach us. We're safe in our stellar nursery, free to grow and evolve and dream, even if those dreams must remain within the gentle grip of our sun's gravity. So the next time you look up at the night sky, see it for what it truly is, not a sea we'll sail, but a painting we can admire. Those points of light are not destinations but decorations, reminding us that we're part of something vast and beautiful, even if we can't touch it all. We are children of the cosmos, made of star stuff, contemplating stars we'll never reach. And in that contemplation, in that very act of understanding our limits, we achieve a different kind of transcendence, not through space, but through knowledge, wonder, and acceptance of our cosmic home. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How big is the universe? In this video, discover the true scale of the cosmos, from the size of Earth and our solar system to the Milky Way, superclusters, and the mind-blowing diameter of the observable universe. See you there.